So we've been talking about the fundamental theorem of calculus. Last time we introduced the first part here. So we're already familiar with the second part of the fundamental theorem of calculus. The part that says we can evaluate a definite integral by using the antiderivative of the integrand. And here's that formula. So this would be fair for the test on Wednesday, but we've been focusing on part one here. And so this won't be covered on the test on Wednesday, part one. Part one will be covered on the final exam. So now for fundamental theorem of calculus part one, there's two things that I want you to think about. First, we're introduced to this new type of function. This is a way of creating functions using those definite integrals that we invented in the beginning of chapter 4. So now we've taken the definite integral, we've made one of the bounds a variable, and that gives us a function. The idea, graphically is fairly straightforward. So let me just draw a little picture here of what's happening. So graphically speaking, so let me throw up an axis here. Starting with some function. So now I'm just going to randomly draw a function. So just randomly. Here's my function f. This is the function f. That's what I'm trying to write. And so now to create this new function using the net area of f, first pick some point, call it A. And now from A here, we'll calculate the net area in any direction. So now if I pick X here, then we can calculate this net area. In this case, it's an area. And we can call that G of X. And it's the net area under the function f between A and X. And if you want to be very precise and mathematical about it, that's how we would write that exact idea. Here, one thing I want to point out, for example, in this picture, if I pick an X here, for example, to the left of A, in this case, this net area would be negative because we reverse directions. So here, this is like any other function. It can be positive, it could be negative, it equals 0. So it's just like any other function, input-output machine, but it has this weird notation. And I remind you, as always, here, the only variable is the letter X. That's the only variable. The letter T is what we call the variable of integration. It's what's typically known as a dummy variable. It's not really there. It's just a placeholder. Eventually it gets replaced. So here's this new way of representing functions. And so the fundamental theorem of calculus tells us how to take the derivative of this new type of function. And so here's very important that you realize for this formula, the bottom bound's a constant. We have our variable up here. And the fundamental theorem of calculus is basically telling us that the derivative and the integral essentially cancel out. And here you can see what gets returned after we take the derivative of the integral is the integrand, the thing we're integrating, but in the correct variable. Here, the only variable here is X. And so here, the integrand gets spit out as a function of X. So, one question is, why do we care about this? Why did we, why do we have to write functions this way in this integral form? We were fine before. We didn't need this integral form at all. So there is a purpose here. So, one result that we immediately get, which will continue in chapter 5, is that we can, using this type of function construction and using fundamental theorem of calculus part 1, we can find an antiderivative of 1 over x. Basically, if we define a function like this, integral 1 to x of 1 over t dt, then the fundamental theorem of calculus tells us how to take the derivative. More than that, it tells us specifically that the derivative of this weird integral function is 1 over x. And, you know, one function that we have not been able to find the antiderivative of was 1 over x. So now finally, because of fundamental theorem of calculus, we're actually able to solve that question. What's the antiderivative of 1 over x? And so, you know, we will name this function, we will give it a very special name. We will call this function here, the integral from 1 to x of 1 over t dt. We will call that function the natural log function. And it will become the antiderivative of 1 over x, and it'll, you know, be a starting point for logarithmic and exponential functions, which will open up a whole other area of calculus. It will lead us right to differential equations. So that's one of the main reasons this is that really important. And we'll continue talking about the natural log in chapter 5. So the other formula I have written down here, you know, at the end of the day, this formula here is just a derivative formula. At the end of the day, that's what you should see. So given a function of x, you know, it's a slightly weird looking function of x, but it's still a function of x. Fundamental theorem of calculus part 1 tells us how to take the derivative of that function of x. So I also wanted to give you the chain rule version of this differentiation formula. So if you take a look right here, what we're trying to differentiate, this looks identical to our function in the fundamental theorem of calculus, except the upper bound is not an x. If you look here, the upper bound for this function is now u of x, where u of x could be any function. It could be as simple as x, but it could be cosine of x or x squared or square root of x, whatever. So the question is, the fundamental theorem tells us how to take the derivative when the upper bound is an x. The question is, how do we take the derivative when the upper bound is not an x? And so the answer is, we just use a chain rule. If you look very carefully, this function here is basically the function g of x, but the x, this x part here, has been replaced with cosine. So or u of x, sorry, cosine, sorry. The next example we're going to do has a cosine. So here, if we take this function g of x and right up here, where we have an x, replace that x with the u of x, we'll get our integral from a to u of x. And we can also think of it as a composition. We can think of it as g, where the x was replaced with u of x. So we've got g of u of x. And now we know how to take the derivative of a composition. We use a chain rule. So right here's the derivative of the outside. And we already calculated the derivative of g. G prime is equal to f of x. That's what the fundamental theorem of calculus tells us. So g prime of u of x is going to look like f of u of x. And then the other term comes from the derivative of the inside. So here, u of x is the inside function. So u prime, that's the derivative of the inside. So, you know, don't worry about this chain rule too much if it looks like a whole bunch of mess. We'll come back to this in 1 second. When I do the examples and we have actually concrete functions in there, it'll look a whole lot less abstract. For right now, what you should really be keying in on is that this is a function of x. It's an input-output machine. And that the input variable is right here. These two, you know, whatever goes in here needs to go in here. Okay, so the best way to now, you know, show you fundamental theorem of calculus part 1 is to now start doing some examples. So here's the first problem. It says if g of x is equal to integral 0 to x radical 1 plus t squared dt, find g prime of x. So the first thing I want to warn you about, remember I always say calculus is limit problems, derivative problems, integral problems. Here, we should recognize that this is first and foremost a derivative problem. It's not an integration problem. And, you know, the one thing I would really warn you against doing is to try to evaluate this integral. There's no point in evaluating the integral to then take its derivative. You know, that's like moving forward 2 steps and then taking 2 steps back, you know. So here, not to mention, we don't know how to do this integral. So here it's really important to realize you know, this problem, we should never try to do the integral. So here we're going to take a derivative of this weird integral representation of a function. Here, because the integrand is continuous, I can just directly apply the fundamental theorem of calculus. And I mean, it's really straightforward. There's literally no math here. All I'm doing is copying down the integrand and replacing the dummy variable with the actual variable x. So here, what you should kind of see is that the derivative and the integral canceled each other out. I ended up just getting back the integrand, the thing I'm integrating, except it needs to be in the correct variable. It can't be in the dummy variable. Here, the correct variable is x. And so this is, you know, the integrand with the dummy variable replaced with x. And there's literally, it's just a notational thing. We've not done any math as far as I can tell. All we've done is apply the fundamental theorem of calculus, which gives us this result for free, that the derivative and integral cancel out. So what's tricky, I think, is just getting confused to the game that we did, getting used to the game that we just played. And of course, starting to think of this, really looking at it, really realizing, oh, that upper bound is a variable. So this isn't just a regular definite integral. This is actually a function of x. So now I made the problem slightly more complicated. So what's the difference? Now, instead of just x in the upper bound, we have a function of x in the upper bound. We have cosine of x. And that could be any function. That could be sine of x. That could have been x squared, whatever. So here, again, you know, I remind you, first and foremost, this thing here, that's a function of x. For each x we plug in, that expression evaluates to a number. It's an input-output machine. We want the derivative. So here, I'm going to relate it to the previous example. If I define g of x to be integral 0 to x, not cosine x, 0 to x, radical 1 plus t squared dt, then I can write the original problem, integral 0 to cosine x of radical 1 plus t squared dt. I can write that as a composition. I can write that as g composed with cosine. So just take a second here, look at g of x. And so now, if I plug in a cosine right here, I'd have to replace this upper bound with a cosine also. Then we end up getting the function we're trying to take the derivative of. And now g of cosine of x, that's a composition. So I do a chain rule. Here I've got my derivative of the outside function. And we know from fundamental theorem of calculus that g prime is the positive square root of 1 plus x squared. So g prime of cosine of x, I'm going to replace the x squared with cosine of x. And then for my chain rule, I need to do the derivative of the inside. So that inside function is this cosine function. Derivative of cosine is minus sine. And so I've written that in the front here. So here's my final answer here. Negative sine x, that's the derivative of the inside. And then the g prime cosine x looks like radical 1 plus cosine squared x. And so you should take some time, let your eyes get used to what they're seeing. You know, take a look at this and compare it with this, and compare and contrast. See how they're similar and see how they're different. Okay? And then realize, you know, this weird integral 0 to x, that's a function of x. And here we're trying to find the derivative of this function of x. So someone is asking, why is it negative sine of x? So remember that the derivative of cosine is minus sine x. And that's just the derivative rule for cosine. So the derivative of sine is cosine, but the derivative of cosine is negative sine. And that's just, you know, cosine is always troublesome that way. And here I repeated the chain rule here. And remember, you just need to learn the one rule. This rule will work. This is the most generic form of fundamental theorem of calculus. Here, if I make this upper bound into an x, then this formula just becomes the derivative integral a to x f of t dx will just be f of x times x prime would just be 1. So this formula will work, is the most general version of fundamental theorem of calculus part 1, which of course you're not responsible for this week, but for the final exam. So here is basically the most complicated version of a problem like this. So I've got a definite integral where the lower bound is a function of x and the upper bound is a function of x. So here, it's really important that we not invent any math. So what do I mean by that? The fundamental theorem of calculus, part 1, requires that the lower bound be a constant before we can use the formula that's given. So here, I first need to do some integral manipulations and make this look like something we know how to take the derivative of. And here I'm just going to use some integral properties. We know you can break up an integral from a to b. I can break it up integral a to c and then c to b. So here I randomly break up the integral at 0. I go x to 0 and then plus a new integral 0 to cosine. And here, as long as 0 is in the domain of the integrand, we're fine. And here the integrand square root of 1 plus t squared is defined for all t values. We don't need to worry about those little details so much right now. But here I use the properties of the integral. I split the integral up into 2, x to 0 plus 0 to cosine. And I want the constant on the first integral to be on the bottom, because that's what fundamental theorem of calculus requires. So I flip the bounds here. And when you reverse the bounds, we incur a minus sign. The end result here, the question is, why are we doing all this? Now I have an integral in the form that fundamental theorem of calculus tells us how to integrate. We have integrals in the form integral with a constant on the bottom, some function of x on the top. Whether it's just x or some more complicated function of x, that's fine, doesn't matter. But now we're in the correct form for applying the fundamental theorem of calculus part 1. So now let me take the derivative. Here's the derivative of the original function. Let me rewrite it. So I split it up at 0 and flip the bounds on the first definite integral, got a minus sign. And now the derivative of the sum is the sum of the derivatives. And now here we apply the fundamental theorem. And it's almost kind of too easy here. The derivative and the integral cancel out. I'm going to copy down the minus sign and the integrand, but I'm going to change the derivative, the variable here, from the dummy variable to the actual variable. So this t I'll make into an x. And so there's my derivative of the first term is right here. We dropped the integral, we copied the minus sign, we copied the integrand, we replaced the t with an x. And then I have the plus symbol right here in between them. And now here's my second fundamental theorem of calculus. Again, what we're kind of seeing in our mind is that the derivative and the integral cancel. What gets returned here, this is a cosine x up here, so I got to use the chain rule version. Okay, so what does that mean? I'm going to write down the integrand, but replace the dummy variable t squared with cosine, the upper bound. That's the derivative of the outside. And then finally, I do derivative of the inside. The inside function is the cosine function. And the derivative of cosine here is negative sine x. So yeah, it's kind of a mess, but we didn't really do that much math. At the end of the day, I only took one derivative. The only place I did any work was right here, when I took the derivative of cosine. Everything else was just understanding the notation and realizing the derivatives and integrals are canceling, and the dummy variables, I can't write those down. They're just placeholders. I need to, have actual variables there, or use a chain rule, in this case, because they have the cosine x up here. So it kind of looks like a drawn out procedure and the notation looks complicated, but it's really not that hard. Like I said, I didn't do very much math, just kind of canceling integrals and derivatives and plugging in at key places. In one place, I did a chain rule. So my very last step here is I factored out the minus sign just because I felt like it. You don't have to. I just factor out the minus sign, put the minus sign of x function in the front of that root term. So yeah, you should take a look at these slides. They're not difficult, but what does require getting used to is this notation. Getting used to this new type of function, and then learning the derivative rule that goes with this new type of function. From here to here, how did that derivative work? And from here to here, how did that derivative work? So I want to end this section 4.4 with a discussion on what's called the mean value theorem for integrals. So the game we're playing now is we're going to try and apply mean value theorem on a function that looks like this, one of these weird functions where it's integral a to x f of t dt. I said this is just a regular input-output function. It just looks weird. It's defined with an integral. Well, if it's a regular input-output function, well, let's apply mean value theorem to it and see what happens, okay? So before we do that, let me give you a seemingly random definition, but it's not random. We want to define the average value of a function on an interval to be, so start by looking at the right-hand side. We find the net area, integral from a to b f of x dx. Here a and b are constants, and we take this net change and divide it by the length of the interval. So we're basically trying to, on average, come up with a number that says how much change there is, net change there is. So here, a notational thing to watch out for, f sub AVE, the AVE stands for average. This notation represents the average value and is a constant. So that part you have to be careful. Typically, when we have little f, it's a function, like little f of x. But here, there's no of x. It's just the letter f with the subscript AVE for the word average. So be careful. This expression on the right-hand side, if you really look at it carefully, completely evaluates to a constant. The dummy variable, a and b are constants here, so there's no variables. So the way I like to think about this seems quite random, but the way I like to think about it is I take the b minus a and put it on the other side, and then that gives you an equation like this, that the definite integral equals the average value times b minus a. So I interpret the average value as being the height of a rectangle where the area of the rectangle will be the same as the net area of the integral. So here, let me draw a quick picture just to show you what I mean. So suppose we have, and I'm just going to make up a function. So suppose we have a function like this. It's just like that. And so here's A, and here's B. The average value is basically some height where if I calculate the area of this rectangle, so this height here is f sub AVE. So here I'm going to label the y value here. So the height here of this blue line is the average value, f sub AVE. And it's a constant. It's a constant, okay? There's my average value. And if you calculate b minus a times the average value, that area will be the same as the area under the curve. So that's, to me, that's how I think about the average value. If I wanted to find a rectangle that was with b minus a and had the same area as this integral a to b f of x dx, what would the height of that rectangle have to be? The height would have to be the average value. I'm gonna let you think about that, but anyway, that's one interpretation of the average value, that it would be the required height for the rectangle of width b minus a to have the same net area as this, integral a to b f of x dx. Okay, having said all that, here's the mean value theorem for integrals. It basically says that there exists a number c in the closed interval such that f of c equals the average value. Basically, that the average value is one of our range values of our function. And, it's kind of a random result and not that interesting. I think what is interesting about it is the proof, because basically, once again, we're working with this kind of weird new type of function. And so, it's a very simple idea that, oh, well, if this thing is a function of x, let's apply the regular mean value theorem to it and see what happens. And so that's all we do. So, for the 100th time to bug you, remember, x is the only variable here, and that t doesn't really exist. It's just a placeholder. This letter t could be any symbol as long as it's not an x. I could have integral f star d star. That's fine, as long as it's not an x. Okay, but I hate to do that nonsense. Okay, so let's apply the mean value theorem. I claim f of x is continuous. Why? Because it's differentiable. How do I know it's differentiable? Fundamental theorem of calculus tells us exactly that this function is differentiable and how to find the derivative. So differentiability implies continuity, so I can apply mean value theorem. Mean value theorem now says there exists a number c in the interval a to b such that capital F prime of c equals capital F of b minus f of a. But f prime of c, capital F prime of c, is exactly little f because of the way capital F is defined. And because of our fundamental theorem, we're taking the derivative of an integral. So here, I'm going to get back little f of c, like the left-hand side of the equation. I'm going to get back little f of c on the left side. And one last comment here to finish the proof. F of b minus f of a, again, fundamental theorem of calculus tells us that equals the integral from a to b of little f of x dx, where capital F is the antiderivative of little f. So here, this numerator, I can write in integral form this way. And so now if you look on the right-hand side, that's exactly the formula for what we're calling the quote-unquote average value. So I think they did the mean value theorem for integrals first. They came up with this expression first, and then they said, oh, let's define that to be the average value. So I think that's where average value even comes from. It seems random, but I think really it comes from first they did the mean value theorem of integrals and realized they're getting this result, and then they decided to give this expression on the right-hand side of definition, call it the average value. So yeah, it's kind of interesting, the proof, just to work with these interesting types of functions, but certainly you shouldn't worry about the proof. What you should know is the definition of the average value and the general statement here. But again, it's not that important, and I wouldn't worry about it now at all. So here, let me do an example just to show you this average value in business. So here we're given a function and an interval, and we want to find the number c in the interval such that f of c equals the average value. So first, I need to find the average value. So here, I first do these calculations here to find the average value. And in this case, b minus a would be 1 minus minus 1. So here, b would be 1 and a would be negative 1. So b minus a is 1 minus minus 1. I get, 1/2. Integral minus 1 to 1. The function's x squared. And now we can use fundamental theorem of calculus. I know an antiderivative is x cubed over 3. And then, x cubed at 1, you get 1/3 minus, and you plug in the minus 1 for x cubed. That's a minus. So I get 1/3 minus minus 1/3 is 1/3 plus 1/3. You get a 2/3. And then there's the 1/2 that was in the front from the 1 over b minus a. So the 2's cancel. And so now I have my value of the average value of the function. So now I'm going to plug in c into the function, the letter c, you could call it x or t or whatever, and just set that equal to the average value. And the function here is the parabola x squared. So here we have c squared equal to 1 over 3. So here the answer is the square root of 1/3 or plus minus 1 over root 3. And then because I'm I'm kind of a math nerd, I proved that plus minus 1 over root 3 is in the interval minus 1 to 1. You don't have to do that, and you can completely skip that part. You know how I am. And so here, the value of c, such that f of c equals the average value, is plus minus 1/3. And geometrically, what does that mean? So I graphed it here. So what we're saying is that this shaded region here under the curve, the area of that shaded region and the area of the rectangle are identical. The way I like to think about it is if we broke the wall here of the function right here at 1/3, right here at 1/3, if we cracked a hole in it, then all of this area here would leak into this section right here. And all of this area would leak into this section right here and fill it up perfectly. And you get this. So, the challenge for you is visually, when you look at these two, do the shaded region, does that seem to be the same area? It's visually challenging. It maybe does or does not, but mathematically they are the same. According to the math, they're identical. So I'm going to let you think about that. That ends section 4.4. And so now in section 4.5, we want to now continue to do antiderivatives, continue to evaluate integrals using antiderivatives. So now we just want to be able to solve more and more complicated problems. So let me introduce you to a technique for solving definite integrals called U substitution, the letter U and the word substitution. So specifically, it's for a very specific type of integral. So if we have an integral that looks like this, integral a to b, f of g of x times g prime of x dx. We specifically want to ask the question, how do we evaluate this specific type of integral? So we want to use the fact that we here know that capital F is an antiderivative little f. That's what we're assuming here. And we know that in a definite integral, the variable of integration is just a placeholder. So what I want to do is play a game and change what the integral looks like. I'm not going to change what it is fundamentally, just change what it looks like. Maybe I can make it look like something that's easier to integrate. So in this particular discussion here, the trick we're going to use is let u equal g of x, okay? In general, when we're actually solving, problems from a practical point of view, it may not be obvious, okay? There's a fair amount of trial and error involved. But in this case, because the g of x is in here, inspired by that, I'm going to let u equal g of x, and I want to completely convert this integral from the x variable. I want to convert it to the u variable. Why? Because maybe it's helpful. Maybe it'll help us calculate the integral. So one important thing to remember is now that I'm going to replace g of x, but I also need to think about d of x. Okay, I need to replace that also. So using this equation, u equal to g of x, we calculate the differentials. Remember differentials? So here you get du equals g prime of x dx. And by, so-called coincidence, if we look in our integral, I have a g prime dx term exactly. So this is good. One final part that I need to transform are the bounds. Here, when we say a and b, be careful. We really mean x equals, in this case, because it's a dx integral, and here x equals b. I'm no longer in the x variable. I'm now switching to the u variable. So I need to also switch the bounds. How do we switch the bounds? Well, when x equals a, I simply plug it right into here for x. So when x equals a, I get that u equals g of a. Because I'm just plugging right here for x. And when x equals b, I'm just going to plug right in here for b. I say u equals g of b. So these two equations now allow us to convert the bounds. So we've converted the bounds, we've converted the dx part, and now we can actually convert the whole function. So let's transform the variable. So here's the word, the official, what we're doing here to this integral. We're calling it a u substitution, but what's really happening is we're transforming the variable. And this equation u equal to g of x, that's a transformation. That's what's known as a transformation. So transforming the variable, the integral, look what happens. We go from the x variable, integral from a to b, f of g of x, g prime of x dx. So I'm going to replace the g of x with u. I'm going to replace the g prime dx with du. And I'm going to replace my bounds that are in terms of x. I'm going to replace them with bounds that are in terms of u. And so when we do that, the new integral looks like this. I've transformed the integral. So integral a to b, f of g of x, g prime of x dx is now integral g of a to g of b, f of u du. That's a transformed integral. And the whole reason we've transformed the integral is because we hope it's easier to evaluate this integral. And in this case now, we can use the fact that here we're assuming that we know the antiderivative. So now I'm going to use the fact that the antiderivative of little f is f prime. And so this integral now becomes integral from g of a to g of b, capital F prime of u du. And now using fundamental theorem of calculus, we know we can evaluate this definite integral using an antiderivative of capital F prime, namely f. And now you do that, f of u evaluated at the upper bound minus the function evaluated at the lower bound. I get f of g of b minus f of g of a. Please, keep in mind, a and b are constants, so this entire right-hand side is a constant, as it should be, because the left-hand side is a definite integral where everything is a constant. B is a constant, A is a constant. This whole left-hand side evaluates to some net area. So yeah, using this transformation, using this u equal to g of x business, we are able to solve this definite integral. And in fact, this strategy works for antiderivatives, for integrals without any bounds, right? Antiderivatives. Again, if I let u equal g of x, so here's my transformation. Look what happens to the antiderivative. It converts from, so here, the g of x here becomes the letter u. And so this becomes little f of u, but little f equals capital F prime. So I'm replacing little f of the variable u with capital F prime of u. And as before, g prime of x dx is just equal to du by differentials as before. So here, g prime of x dx is just du. So yeah, once we transform, so here's the du, g prime of x dx. So yeah, once we transform the integral, you can see it's something we can use fundamental theorem of calculus for, or it's, in this case, we don't need fundamental theorem of calculus because it's not a definite integral. Here we can just find the antiderivative as f of u. And the only final comment to make here is that since the original problem was in the x variable, I need to replace u with what I originally substituted it for, which was g of x, and get my final answer here in terms of the x variable. So again, using u substitution, we're able to calculate this antiderivative. And of course, we can check our answer by doing a derivative. Here we would do a chain rule. The derivative of the outside is capital F prime of g of x times g prime of x, but capital F prime equals the little f. And so we get back our integrand. So yeah, this formula we've verified is true and correct. So this is an example. This is sort of the theoretical basis for u substitution, which is basically, another word for transformations, integral transformations. So let me just show you the generic, slides here for the substitution rule. So here, this isn't really that helpful. When we actually start doing examples is what helps. So here, if we let u equal g of x, then we can transform the integral of the antiderivative f of g of x, g prime of x dx to antiderivative f of u du. And remember, this is only helpful if I can now calculate this second antiderivative. So in theory, hopefully we've made the problem simpler and therefore easier to solve. If this f of u du, if I can't solve that, then this transformation didn't work and was not helpful, and I'm back to square one, and I need to try a different transformation, just from a theoretical point of view. For the definite integral, it's the same. We're using the same transformation. The only difference is here we have bounds. And so we can use the transformation to also convert the bounds into the new variable u. One of the big mistakes I see when students do u substitution is they forget to convert the bounds. They use the function in terms of u, but with the bounds that are for the x variable. Remember here, this dx here is telling us these bounds are for the x variable. So a couple of comments here before I show you a quick example. So the technique may not always work. It's just something we're trying. And certainly this does involve some amount of trial and error. It's not necessarily obvious what the correct substitution is necessarily. As I mentioned already, don't forget to transform the bounds of integration if there are any. So when you have a definite integral problem and you're doing a u substitution, you want to really be careful which variable you're in. If I'm in the x variable, I want to use bounds for x. If I'm in the u variable, I want to use bounds for the variable u. And I'll show you an example here in a second. Finally, I want to make a comment about a very common, understandable, and normal mistake that I don't want any of you to make. We must never use the u substitution, the trivial substitution u equal to x. I say trivial because we're not changing the situation. When we do u equals x, I'm just swapping out one squiggle for another. I haven't made the problem any easier. I've just, replaced variables. I've replaced the x squiggle with the u squiggle. And it's a very natural mistake to make, especially in the heat of a test and a student's not sure what to do. But don't do that. Don't say u equal to x. It's not going to help you at all. So, all right, the best way to do u substitution is to do a bunch of examples. And you'll see this lecture is 13 slides long. It's very long. Typically, our lectures are 8 to 9 slides. Anyway, we'll talk about this today and on Friday as well. So I start out with a very easy problem. Quote unquote easy, it's not easy. So here it's the antiderivative 2x times quantity x squared plus 7 cubed. So first, I recognize this as a integral problem, not a derivative problem, not a limit problem. Second, I remind myself I can't just do, this is not equal to the integral of 2x times the integral of x squared plus 7 cubed, okay? So in theory, one thing we could do, which is like a horrible idea, is to expand out the cubed term, distribute the 2x, and then integrate term by term. So that's a lot of work, and is unnecessary. It's a lot of work that we could just completely avoid if we work smart here and use U substitution. So let me do this problem. I'm going to show it to you in two different styles. I'll use U substitution in both cases, but I'll just do it in a slightly different style. And you should see which style you like. Do it one way or the other, or maybe learn how to do it both ways. Okay, so what I'm going to do is I need to solve this antiderivative. Just by looking at it, I don't know the answer. It isn't one that's obvious. It isn't like antiderivative of cosine or antiderivative of x squared. It isn't one that's obvious. So I need to try some strategy. The only strategy we have in Calc 1 is U substitution. If we don't know the antiderivative right away, then we're doing a U substitution. So here, I'm looking for patterns. I'm looking at the integrand, and I'm asking myself, is any part of the integrand a derivative of another part? So here I notice that 2x, for example, is the derivative of x squared plus 7. It's also the derivative of x squared, but I'd like to simplify this integrand, so I'd like to combine as many terms into a single symbol as possible. So here, if I let x squared plus 7 equal u, I've packed two separate symbols, the x squared and the 7, into one symbol, and I've kind of made that simpler. So I'm going to let u equal x squared plus 7. And then, one thing that's really important is to immediately figure out what's your dx going to be. So here I calculate du, and I get du equals 2x dx. The derivative of x squared is 2x, and then you slap on a dx. And 2x dx matches. Look, I've got a 2x here and a dx here. So it looks like it's going to match. It looks like we're going to have a successful transformation. So what do I mean by a successful transformation? We have a successful transformation when we are able to completely replace all of the x variables and convert those into u variables, the letter u. So let me show you now here. This x squared plus 7 that's inside the q, that I'm going to replace with our letter u. The 2x and the dx, let me first group those together. And when I group them together now, this entire 2x dx, I'm going to replace with du. And so here's the transformed integral. What you should see is that this integral here, which is in terms of x, has now transformed to a simpler integral in terms of u. And u cubed, I know the antiderivative of. That's u to the 4th over 4 plus c, right? This is the indefinite integral. Finally, as I mentioned before, the original problem is in terms of the variable x. So I need to go back to the original variable x. So right here, the u to the 4th, I'm going to replace it with x squared plus 7. So when I do that, I get my final answer here. Here's our antiderivative worked out using quote unquote u substitution. So the alternate method is not much different. The only difference here is I'm going to solve for dx in terms of du and substitute. These are just mechanical differences. So let me show you what I mean. I still use the same u substitution, but u equal x squared plus 7. And then I still calculate du is 2x dx. But now here, this is different. I solve for dx. So I'm solving for this expression right here, dx. See, dx is du over 2x. Okay, what do I do with this? I'm going to now substitute. I'm going to replace the dx here with du over 2x. So right here, this dx, I replace with du over 2x. And as before, the x squared plus 7 part, this, I'm going to replace with u. Now do some algebra here. The 2x's cancel. There's this 2x that was there from given, and then when I solve for dx, I got du over 2x. Those 2x's cancel. And here's my successful transformation. It's successful when all the x variables are gone and I only have something that's in terms of u. And now the whole point of this was hopefully this is something I could find the antiderivative of. And yes, U cubed, we know the antiderivative is u to the fourth over 4 plus c. And as I mentioned, the original problem is in terms of x, so the answer should be in terms of x. So I replace u with the original thing that we substituted u for. So up here, I plug in for the x squared plus 7. And so we get the same answer, 2 different styles. Just depends what you like to do, which you're more comfortable with. I typically will do method number 1, but I can do it both ways just because I like to be able to solve things in multiple ways. And finally, of course, we can verify that our answer is correct by taking the derivative, right? Here, the derivative of this expression should give us back our original integrand that we tried to find the antiderivative of. So I can take the derivative and you can check the chain rule here. It worked. I was able to verify that it's the correct antiderivative. All right, everybody, I'm going to stop right here. Remember, U substitution will not be on the test this week. This is all stuff for the final exam, so we have time to work on this. Okay, so don't worry about this stuff right now. All right, I'm going to stop right here.